Hello, and welcome to another lesson from Level Up Mathematics. In today's lesson, we will be solving absolute value inequalities. So solving an absolute value inequality is similar to solving an absolute value equation, but the solutions will be expressed as compound inequalities. So let's review compound inequalities. So if you were given a graph like the one below where it says or inequalities, to write an inequality to express this graph, we would see one branch that goes off to the left, it's starting at -2, and a second branch that starts at +3 and goes off to the right. So to express this with a compound inequality, we could say the set of all numbers, which we'll call x, is less than -2, or the set of all real numbers that are greater than 3. So writing an inequality for a graph of this type requires this or statement, right? Now, if your segment is connected, then we will have what's called an and inequality. So notice the part of the number line that's shaded are all the numbers from -4 to +3. So we could write this as an and inequality like this. X is greater than or equal to -4 and x is less than or equal to 3. Now we can also express an and inequality like this. -4 less than or equal to x less than or equal to +3. These are both ways of writing and inequalities. All right. So in example 1, it says model each absolute value inequality on the number line and then identify the solution set. So in our first problem, we have the absolute value of x is less than or equal to 3. Now I'm going to rewrite this, excuse me, as absolute value of x minus 0 is less than or equal to 3. So the meaning of this is what numbers have a distance from 0 that is less than or equal to 3 units. So here's 0 on our number line. If I go out 3 units to both sides, here's +3 and -3. What numbers have a distance that is less than or equal to 3? Well, 1 has a distance that's less than or equal to 3 because 1 is 1 unit away from 0. 2 is 2 units away from 0, and that's less than or equal to 3. Same thing with -1 and -2. So the solutions to this inequality lie in between -3 and 3. Now we can write this as an and statement by saying x is greater than or equal to -3 and x is less than or equal to +3. Or we could write it like this: -3 less than or equal to x less than or equal to 3. So all the numbers that are bigger than -3 but smaller than, less than or equal to 3 have a distance that's less than or equal to 3 units from 0. All right, problem B. We have the absolute value of x minus 1 is less than or equal to 4. So the meaning of this statement is saying what numbers have a distance from 1 that is less than or equal to 4 units. So here's the number 1. Now let's count out 4 to the right. 1, 2, 3, 4. Put a dot. And 4 to the left. 1, 2, 3, 4. And put a dot. And we want the numbers that have a distance that's less than or equal to 4. So 2 has a distance of 1 from 1. 3 would have a distance of 2. 4 would have a distance of 3. So all of these numbers have a distance that's less than or equal to 4. So when I draw my number line, I'm just going to connect these. And I'll say x is greater than or equal to -3, and x is less than or equal to 5. Now, to write this as one single inequality, I could say -3 less than or equal to x less than or equal to +5. All right, problem C. absolute value of x minus 4 is greater than or equal to 2. This literally means what numbers have a distance from 4 that's greater than or equal to 2 units. So here's the number 4. If I count out 2 units, put a dot, and then count to the left 2 units and put a dot, I want numbers that have a distance that's greater than or equal to 2 units. So 7 would be a solution because 7 is 3 units away from 4. 8 would be a solution. 9 would be a solution. 10 would be a solution. So we have a lot of solutions going in this direction. Okay. Likewise, we have a lot of solutions going in this distance. So all these numbers that I just shaded have a distance from 4 that's greater than or equal to 4 units. So this would represent an OR inequality. X is less than or equal to 2, or X is greater than or equal to 6. All right. Problem D. We have the absolute value of X plus 2 is greater than or equal to 4. So what numbers have a distance from negative 2 that is greater than or equal to 4? So here's negative 2. I want my distance to be greater than 4, so I'm going to go 4 to the right, 1, 2, 3, 4, and 4 to the left, 1, 2, 3, 4. So I want numbers that have a distance from negative 2 that's greater than or equal to 4 units. So that would be all the numbers in this direction and all the numbers in this direction. They have a distance that's greater than or equal to 4. So X is less than or equal to negative 6, or X is greater than or equal to 2. All right. E. The absolute value of X minus 1 is greater than negative 4. What numbers have a distance from 1 that is greater than negative 4? So here's 1. Okay. Let's say we had the number 2. That's 1 unit away from, that's greater than or equal to negative 4. 3 would be greater than or equal to negative 4. Actually, all the numbers on this number line are all going to have a distance that's greater than negative 4. So we could say all real numbers. That's because distance is either equal to 0 or it's positive. Therefore, what numbers have a distance that's greater than negative 4 units? All of them. So I'm going to shade in the entire number line and put arrows at each end. All right. F. Absolute value of X minus 3 is less than negative 4. What numbers have a distance from 3 that is less than negative 4? So this would be no solution because distance must be positive. So I'm not going to shade the number line at all in this situation. All right. Now, on our second page, let's get into actually solving them. So when solving absolute value inequalities, you're going to solve them exactly like you solved absolute value equations, except for you just remember this phrase, go LA. So the G stands for greater than, and the O stands for or. The L stands for less than, and the A stands for and. So if you have a greater than, your answer will be an or inequality. If you have a less than, your answer will be an and inequality. Go LA. So if you have problems of the form absolute value of AX plus B is greater than C, then you can rewrite that as an or inequality. Greater than or, go. So AX plus B is less than opposite C, or AX plus B is greater than positive C. Now, if you have an absolute value that's less than C, you can write it as AX plus B is greater than C and AX plus B is less than C. Or you can write it a shorter way. Opposite C is less than AX plus B, which is less than C. Those are the two ways to write an and inequality. Now let's practice this. In problem A, we have the absolute value of 2x plus 3 is less than 8. So this is an LA, less than and. So what I'm going to do is I'm going to set it up like this. The opposite of 8, less than or equal to 2x plus 3, and I'm taking that out of the absolute value brackets, is less than 8. There's our and statement. 2x plus 3 is greater than or equal to negative 8, and 2x plus 3 is less than positive 8. So to solve this, we'll subtract 3 on the left, the middle, and the right. And that will give us negative 11 is less than or equal to 2x, which is less than or equal to 5. And then we'll divide everything by 2. Middle, left, right. Now I'm going to write my answer as a decimal. Negative 11 over 2 is equivalent to negative 5.5, which is less than or equal to x, which is less than or equal to 2.5. I'm writing as a decimal to make it easier to plot my solution. All right, so my solution is x is greater than or equal to negative 5.5, and x is less than or equal to 2.5. So I'm going to put a filled in circle at negative 5.5, a filled in circle at 2.5, and all the numbers in between those two are said to be solutions to the inequality. So let me box in my algebraic solution, and then here's my graphic solution. All right, problem B. 6 plus 2 times the absolute value of x minus 5 is greater than 12. Now, notice on this problem, our absolute value expression, this x minus 5, has not been isolated. So before we can solve it, we need to isolate that expression. So I'll start by subtracting 6 from both sides, and that will give me 2 times the absolute value of x minus 5 is greater than 6. Now we'll divide both sides by 2 to get x minus 5 is greater than 3. So now we can see that this is a greater than. So this is a go inequality, greater than or. So x minus 5 is less than the opposite of 3, or x minus 5 is greater than positive 3. So add 5, add 5. X is less than 2, or add 5, add 5. X is greater than 8. So this is my or statement, or my algebraic solution. My graphical solution is I would put an open circle at 2 and shade less than. Then put an open circle at 8 and shade right. So notice an or inequality is going to look like the oars on a rowboat. Or, oars, okay? All right, problem C. 8 times the absolute value of x plus 4 plus 10 is less than 2. All right, I want to start by getting my absolute value brackets isolated. So I'll subtract 10 from both sides. So that gives me 8 times the absolute value of x plus 4 is less than negative 8. Now divide both sides by 8, and I get absolute value of x plus 4 is less than negative 1. Now, remember, distance cannot be less than a negative number. That's impossible because distance must be greater than or equal to 0. So this particular problem has no solution. Therefore, we cannot plot the solution on the number line. All right. All right, problem D. 2 minus the absolute value of x minus 3 is greater than or equal to negative 2. So I'll start by subtracting 2 from both sides. So negative 1 times the absolute value of x minus 3 is greater than or equal to negative 2 minus 2, which is negative 4. Now divide both sides by negative 1. And remember, when you divide an inequality by a negative, you must reverse the symbol. So this would be less than or equal to positive 4. So this is a less than, or an LA inequality, an AND inequality. So to rewrite an AND inequality, we'll say negative 4 is less than or equal to x minus 3, which is less than or equal to 4. So add 3 to the middle, the left, and the right. So negative 1 is less than or equal to x, which is less than or equal to 7. So this is our algebraic solution. So to plot our solution on our number line, I would put a filled in circle at negative 1, a filled in circle for 7, and for AND inequalities, we shade in between the two numbers. And that concludes today's lesson, Solving Absolute Value Inequalities.